Всем привет и добро пожаловать на семинары AIRI. Меня зовут Ковалев Алексей, и сегодня наш семинар будет на английском языке, поэтому позвольте мне переключиться на английский. Hello everyone and welcome to the AIRI Seminars. My name is Alexey Kovalev, and today our speaker is Stamatis Levkiamatis, head of computer science group, computer vision group at MTSI, and he will talk about on learning sparsity promoting penalties via implicit differentiation for image regularization and robust estimation. And his opponent for today, Andrei Kuznetsov, PhD and head of Fusion Lab at AIRI. Without further delay, Stamatis, it's your.
Thank you very much for the invitation. So my talk will consist of two parts. In the first part, I'm going to discuss about learned sparse and low rank priors for image reconstruction. And on the second part, I will discuss about sparse penalties for robust model estimation. I mean, the unifying thing between the two parts is that in both cases, we are trying to learn some sparsity promoting penalties. And we will also discuss how we can efficiently train networks that involve this type of penalties, even though this network can in principle be very deep. Okay, so to motivate the first part of the talk, I'm going to discuss about inverse problems in imaging. So in general, inverse problems appear in many different applications, both in machine learning and in computer vision. So what is the goal of an inverse problem? So we have some type of measurements, and the goal in an inverse problem is to be able, so these measurements typically are distorted or incomplete, and the goal is to recover the underlying signal. So in many practical applications in image processing and in computer vision, the forward model based on which we obtain the measurements can be adequately approximated as a linear model. So while this model, I mean, might seem simple, it is general enough and allows us to express a variety of different tasks. For example, if you check here, what we have, so this is the forward model. This is the set of the observation we have, and A corresponds to the degradation operator. So depending on the form of the degradation operator, we can describe a variety of different problems that appear in computer vision. For example, de-blurring, super resolution, demosaicing problems, MRI reconstruction. So in this scenario, I mean, when we are dealing with linear inverse problems, the next task, apart from having the forward model, I mean, the model that explains how we obtain the measurements, we try to recover the underlying signal, as I explained before. But the challenge here is that typically, because we have, apart from the measurements, they are also distorted by noise, and plus this degradation operator is ill-conditioned, the problem typically is ill-posed. So what this means is that it is not sufficient to have only the measurements so as to be able to go back and recover the underlying signal. Okay, so in order to be able to obtain some solution that can be meaningful either in a physical way or in a statistical way, we need also some extra information. So we need to constrain the set of solutions, because otherwise we have like infinite solutions, in the sense that many different underlying signals can explain the observations we get if we don't impose any other structure in the solution, right? So typically how we solve these problems, we try to express the reconstruction, this recovery, as an optimization problem. And we form like the objective function, which if we minimize, then the solution corresponds to the reconstructed signal. And typically, this kind of loss consists of two terms. So we have the data fidelity term, which is it's task specific. So it depends on the task we are trying to solve. I mean, in particular to the degradation operator. And actually, what it measures the proximity of the solution to the measurements. How close is my solution to the measurements? And the other term, it's task agnostic, so it doesn't depend on the task we are trying to solve, but instead enforces our solution to follow some underlying principle, right? So typically, one very popular regularizer or image prior is a sparsity enforcing prior. So what we mean by that is we expect that if we, the recovered signal, if we transform it in some domain, then the coefficients in this transformed domain are going to be sparse. Some examples of sparse transformations is the gradient domain, where we have like very popular regularizers that enforce this property, such as the total variation, the isotropic or the anisotropic version. And for example, here you can see that if we have some natural image and you do this mapping to the gradient domain, you will see that actually most of the responses are zero, except to the edges of the image that they have a high response. So essentially, this mapping is sparse in this sense. What I also forgot to mention is that when we introduce a regularizer to enforce this type of behavior, typically our regularizer has this form. So it consists of two quantities. Gi is the sparsifying transform, and phi is a potential function which essentially penalizes the response on this transform domain. So in our case, what I described before would be a function that promotes like sparse responses. Another like sparsifying transformation is the wavelet transform, which is widely used in image processing. And for example, it belongs on the standard of JPEG 2000, where you do image compression based on a wavelet transformation. Apart from the sparsifying transforms, another popular regularizer, which enforces sparsity but not on the canonical domain, but on the spectral domain, is of this form. So essentially what you are doing, so you have your original, your image, you extract patches from it, you group similar patches, and then you form a matrix. So because these patches are similar, you expect that the matrix that you have created is going to be low rank. So then you are enforcing your solution to be low rank, but which is actually corresponds to being sparse in the spectral domain, because the low rank, how we measure it, we extract the singular values of the matrix, and based on that, we see whether the matrix is low rank or not. But this is sparsity on the singular vector of the decomposed matrix. Okay, so in our work, what we are trying to do is to generalize this concept and not use some fixed transformation like the gradient operator in total variation or the wavelet transform, but instead learn a mapping and then enforce this mapping to be sparse. And we do that based on training data. So there are like, the challenges is like, how do we define this, how do we parameterize this regularizer? And the idea is that, okay, in general, the sparsifying transform should be a linear transform so that the problem can be solvable. Because if we have a non-linear operator, it will be much difficult to attack it and solve it. So this is like a standard approach. We model G as a linear operator, and then we have the potential function, which we decide to express it as a weighted LPP norm. So what is an LPP norm? actually, it's not really a norm, it's a pseudo norm because P here, so imagine the LPP norm is you take the absolute value of every element of the vector, you raise it to some power P. This should be greater than 1 or equal to 1. And then you sum all the values and you take 1 over P of the results. So this would be the LPP norm, right? LP norm. LPP means that we don't take this, but we take the result squared to P. So we get rid of the 1 over P on the sum, right? Now you can choose P smaller to 1. So this is not anymore a norm. But why we choose that? Because it enforces sparsity better. And on top of that, we use weights on this parameterization. So you see here, you have some weights. And what is the idea? The idea is that if I want to enforce sparsity, you can, let's say you have a vector that has like some very big values and the rest are just a few big values and the rest are small. So actually, if you try to enforce sparsity in a uniform way, you are going to try to change all the values in your vector. But actually, it makes more sense to try to reduce the small values. So this will be easier go to 0. So you will achieve some certain level of sparsity. And don't care at all about the big values, because even if you reduce them, they will never go to 0. So the purpose of the weights is to give like some more attention to values that they are really going to help you to obtain this type of sparsity. And the same thing, we do it also on the spectral domain. And actually here you can see an example where we were talking about like a vector of 2. So for different values of P and different weights, we can model different patterns. So essentially this parameterization, it's rich enough to be able to model different properties that can be learned from the data. Okay, so now, I mean, we have somehow parameterize this sparsity promoting penalty, which will serve as our image prior. But now the question is that this is not enough. The next step is based on this image prior to form a loss that if we minimize, we are going to recover the solution. So now the big question comes, how easy can we solve this problem, right? So in general, this objective function is not I mean, you could try to solve it by doing some standard gradient descent, but this kind of method is going to converge very slowly. Plus, you have another issue. You need to tune some parameters. For example, the step size of the gradient descent. So, or you need to do line search so that you make sure you are not diverging. So this is not a good technique. What you can do instead is to follow the majorization minimization strategy. So for those that are not familiar with this strategy, what is the idea? Imagine that I have like a loss function, which is very, it's not like canonical, it's very irregular and it's difficult to minimize. So the strategy is that, okay, I'm not going to work directly with this graph and this function, but instead what I'm going to do, I'm going to find an upper bound, which is easier to work with. So originally, here, for example, I find an upper bound, which is easy because it's bell-shaped, it's easy to find the minimum. I minimize it, I find the minimum, and based on this new minimum, I find another upper bound. And I minimize that. And by doing that in a successive way, at the end, you are going to find either the global minimum if the function is convex, or a local minimum if it's not convex. So in general, this strategy is very popular and very powerful. And for example, the EM algorithm, expectation maximization algorithm, is one instant of this technique, but it's opposite. Instead of majorization minimization, where we do minorization maximization. So we find a lower bound and we maximize this lower bound. Okay. So in order to solve this type of problems where the loss function is not easy to work directly, we follow this. So now the question is, how do we find an upper bound which lead to a simple problem to solve? So this is like also one key challenge. And for that, we have derived for both cases, whether we are working with the sparsity promoting on the low rank promoting priors, we have found in both cases tight quadratic upper bounds. So, which we have here. So now that you have quadratic upper bounds for the image prior, we notice also, and why we choose quadratic upper bounds, because if you notice, the first term, under the assumption that the extra noise is Gaussian, is going to be a quadratic. So if I have a quadratic upper bound for this function, quadratic plus quadratic, the overall function is going to be quadratic. And this is very good news, because we have tools, very efficient tools, to solve this type of problems. So always have in mind that in optimization, it's a game where you try, if I have a very difficult function to minimize, I try to decompose the problem in simpler problems where I can solve. So this is one instance of this strategy. Now I don't have to work with this very difficult prior, but instead I have to work with a quadratic function. So, and as I said, what we do, we find the solution iteratively, we solve one problem quadratic, then based on the solution we create another quadratic problem, and so on and so forth. And the nice thing about the quadratic loss is that actually it has an analytical form. Of course, in practice, we don't use this analytical form because this matrix that you need to invert, it's of like huge dimensions, millions by millions. But still, what we can do, and because of the special structure, this matrix is symmetric and positive definite. Typically, what we are doing, we are using CG, which is a method that can solve this type of linear system iteratively without the need to have access to the matrix itself. The only thing you need is to be able to compute the product of this matrix with a vector. So essentially, what we are doing, we're solving, if this matrix, let's call it A, we're trying to solve the linear system A times xk plus 1 equals this. And we use CG to solve that. So essentially, now, based on what I described, we can express this series of operations as a computational graph. And because we iterate, so one block is like one solution of a quadratic problem, and then you have a recurrency because the output is used to create the problem of the next stage. So actually this motivates us to express everything as a network, right? And if you do that, now, as I mentioned in the beginning, the goal is to learn the transformation, the sparsifying transformation, and the weights. So actually, if you see here, what we have like a feature extraction module, which takes your solution, maps it to some learned domain. Then, based on that small network, you predict the weights in the sparsifying penalty, and you use that to solve using. Okay, here we're using preconditioned CG, which is a faster version. You solve the problem, you obtain the solution, and then you fit. So essentially, the quantities that we need to learn is, first of all, the weights, and these we modeled as a lightweight network that gets as input the previous solution and predicts the weights. The p-value in this LPP norm, which we constrain to be between 0.4 and 0.9 help training. And I forgot to mention, okay, because this is iterative optimization, you need some initialization. So what we do is like we have a very small network that it's doing a reconstruction without a sparse prior, but actually this we use it as the initial guess. Okay, so and typically, I mean, as I said, you can unroll, so you have like different number of steps. So if, let's say, you have 15 steps, which is adequate number of iterations so as to reach a good level of your solution, then because in every step we are using CG to solve this linear system, then you will have almost 1,500 iterations. So this is now, like the question is, okay, if I have a network which consists of 1,500 individual operations and I want to backpropagate, then I have a big problem, right? Because you can have issues like exploding or vanishing gradients. Also, you need a lot of memory to do backpropagation through time. So the question is, can we solve that challenge? Can we still use, because, okay, so far I discussed the motivation, how we create this network, but now the key question is, can we train it? And the answer is that actually, yes, we can train it because of the properties of the network. So since we are having this approach of like majorization minimization, and because we end up solving a series of linear systems, we have convergence guarantees for this particular problem that we are going, after running the algorithm, we are going to reach a stationary point. So actually, we don't even need to run 15 iterations. We can run as many iterations as we need to converge to a solution. So, since we converge to a solution, then we can use the implicit function theorem and backpropagate without having to keep any intermediate results. So this is the idea of implicit differentiation, because the point here is that we don't need to do the naive backpropagation where when we do the forward step, we need to save all the intermediate results. Now we run as many steps as we need. We have a solution, and because this solution is a stationary point of the original problem, we can backpropagate based on the optimality condition. So in our case, the optimality condition, so if X star at the end is the stationary point, should be that. So now we can differentiate with respect to the optimality condition, and we can find so what we need in order to do backpropagation and train our network. We need the gradient of the output with respect to the network parameters, right? So the nice thing is here in the optimality condition, what you have is like you have the output of your overall network, and as a function and the parameters of the network. So if you use the implicit function theorem, you can differentiate and find that the gradient of the output with respect to the network parameters is given by this form. So if we want now to backpropagate, we need to backpropagate, and we need the information of the gradient of the loss function that we use to train our network, right? So essentially, this gradient is going to be multiplied with this quantity. So what we need? First, we record, after we run the forward step, we obtain X star. Next, we take X star and we pass it as an input to an auxiliary network that is performing this type of operation. If we do that, we record the graph. So now we can do a backpropagation on this simple auxiliary network, and we have this gradient and this gradient. So now we can use this system. So essentially what we are trying to find, we're trying to find the product of this matrix times the incoming gradient from the loss that you are using to train your network. But this, actually, you can cast it as a linear system because we don't want to do the inversion. So we solve this problem. So essentially we find this quantity, the inverse times this. So U is going to be the inverse of this gradient times this gradient. So after we find that, we do vector Jacobian product of this quantity with U, and we compute all the necessary quantities. So actually, now, I mean, the key message is that even though if I unroll my network, it can be very deep. In theory, it can be like infinite depth until you converge. Then you don't need to save any intermediate information. The only thing you need is to find the solution and then feed it as input to an auxiliary network that essentially explains the optimality condition of your original problem. And then you can backpropagate through that. So to validate, I mean, these ideas and see how these networks can compare with respect to networks that have been designed specifically for some of the problems that I mentioned before, we have tried like different setups. So here, for example, we are learning essentially only 600 parameters which correspond to the sparsifying transform. We don't learn the penalty. Instead, we use L1. And we learn only G. And this is like 600 parameters. Another scenario is we learn just P and G. So we use LPP, or SPP means Saturn P norm, which is LPP on the singular values of your matrix. So if we are considering the low rank. So these essentially are very small networks in terms of parameters. And here we again have like different scenarios where we learn the weights of the parameterization that I presented before. But still, and here we also learn P, here it's fixed. But still, we have like the network parameters are relatively small, are around 0.3 million. So compared to the modern networks, this is like a tiny network. And we compared on different tasks, for example, color deblurring. So these are results on real images with real blur. Typically, what we are doing, we are using an external method to estimate the blurring kernel. And after that, we use this the estimated blurring kernel to do the deconvolution. And if you see, if you compare, so IRCNN and DWDN, 2 years ago that we were doing these experiments, they were considered state of the art. But you see that their sizes are like 5 and 7 million. While our network is like the largest version is 300,000. And still the results are comparable and in many cases better. What is the message here? That if you carefully design your network and your problem, you don't need to have like a huge network, but you can have something that it's smaller, more efficient, but you need to take into account like the problem you're trying to solve, and also be a little bit thoughtful how to design it. We also have results on color super resolution. And again, okay, in this scenario, we are not really state of the art, but we are like quite competitive. And we have also tried it on different problems, like not only on photographic images, but also on medical images. For example, MRI reconstruction, you can see it as a problem of in painting, but in the Fourier domain. Because the way MRI works is that you have a pattern, a sampling pattern where you are sampling some of the K-space coefficients, which is essentially the Fourier coefficients, and you try to recover the missing ones. So what you see is that this is like a standard approach, which is a back projection, which is used even now in modern scanners. It's very, very simple. But with a little bit of effort and a small network, we can actually get very good results with not like either a lot of computational additive complexity or memory. So in general, we get very good results without having to create like a very huge network. And another important point is here, I mean, you can see also that the network, after we train it, actually it is also converging to the solution. So let me play it again. So here what you see is how the first graph shows the relative error between the current and the previous solution. So you see that actually this drops. The middle graph shows how this is the overall objective decreases, which is actually monotonically decreasing according to the theory, because in every time we have an upper bound, we minimize this upper bound, and in general, the MM framework is monotonically decreasing. So it guarantees that the loss from one step to the other is going to decrease or stay the same. And the last shows how the PSNR with respect to the ground truth. So as we reduce the loss, the quality increases. Another point is that depending on your budget, you can stop early. I mean, after we have trained, you have the flexibility to run your network depending on your budget. If I run it on a very powerful engine, I can run a lot of iterations to make sure that I get the best possible results. But nobody prevents me from running a small part. If I want, for example, to deploy it on a smartphone that I don't have the budget, or I cannot wait for a long time to get a result, I can run a few iterations and then I can show like a preview to the user. In the background, I can continue or I can stop. So the nice thing on these kind of solutions is that you can stop early, you can run more iterations, so you have this flexibility. Because most of the networks are feed forward and they have a fixed number of steps that you need to do to produce the output. Plus, another important point is this recurrence architecture has the advantage that if I have my original input is not severely degraded, because of the way I'm solving the problem, the solution will converge faster. So I don't have to run a lot of iterations. On the other hand, when you have like a big network, it's going to run the same number of operations, either you are close to the solution or not. So it doesn't matter. You are going to run like a fixed budget of operations. While here, you have the freedom to adjust. And with this, I finished the first part of the presentation. So maybe I can take some questions and then we can move to the next one.
Yes, thank you very much, Stamatis. It's a very interesting talk, especially when we every day meet papers that are more engineering-like than deep understanding-like, especially for such general tasks like denoising, deblurring, and all this stuff. I have several questions, actually. I will leave maybe two of them, which are most interesting for me. You showed the overall architecture where you selected two types of tasks like MRI and all the other stuff in comparison with the VPN architecture selection. So sometimes you select UNet architecture in the paper, and sometimes you select RFDN.
Yes, yes.
How did you estimate which type of architecture can be useful for learning
Experiment. So
Yeah.
actually, yes. The key point here is that in our network, we need to have these weights that they give a different weight on different elements so as to penalize and enforce better sparsity. Unfortunately, here it's more like a question of design. Which network can predict better? So we have tried RFDN for like photo restoration because the RFDN architecture seemed to give better results because, okay, I have to be honest, we experimented a lot. It's not like we tried one network and everything worked perfectly. For the MRI, it seemed that because we tried also RFDN, it was not as successful, and we tried UNet, and it was. But yeah, here you have the freedom how to choose this weight prediction network. I don't have like unfortunately there is not a single formula that okay for this you have to. It's a matter of experimentation.
Something like an ablation study for
Yes,
this point,
yes,
because it
yes.
seems that specific domains like, for example,
because
remote sensing can use another architecture.
Because
and so on.
if you see here, I mean, what is the goal of this network? You have some input, like from probably the previous iteration, and the network needs to predict what score is going to give to these elements so as to enforce better sparsity. So it's a bit of a prediction task. To be honest, okay, we didn't spend a lot of time to investigate different architectures. We tried RFDN, we tried UNet, but I guess in this direction, more research can be done. What is the proper way to have this type of network to do the prediction?
And the following question around this is that when we take some specific domain of images, for example, MRI, we have some following task-specific, different specific tasks like MRI segmentation or MRI classification and all around this. How can we select the way of deblurring or solving tasks around this domain when we need to solve some more specific tasks around these images?
Yeah, that's a very good question. So actually, the ideal scenario, because one thing is that we are doing deblurring or we are doing super resolution, but this can be seen as an intermediate processing for a later task.
Yes.
So ideally, you should train your network end-to-end for the task we are trying to solve. Because, for example, let's say I want to do segmentation, right? And I have a blurry image. Deblurring works well for the users, for our eyes. But it doesn't mean that it retains all the information which is necessary for the network to do the best segmentation. So, in my opinion, the best way is that, like, you can even avoid completely doing deblurring, but train on real data with this kind of distortions to learn how to do, because the network internally will learn to extract information or encode the existing information in such a way so that it can solve the problem efficiently. Now, I mean, if you do deblurring and then you train your network, there is a gap in the sense that, okay, I'm optimizing with respect to one criterion, and then I'm using this output, which is optimized for this criterion, to solve a task which are not necessarily correlated.
Yeah, it's similar to one of the latest slides when you said that if a user is ready to use this way,
exactly.
he can stop here.
Yeah, exactly. So the whole thing is that either if you have like one task specific, it's better to do it like that. I mean, here we were considering like deblurring super resolution because there are also these applications for the user you want to do. But for example, let's say you want to do object detection. I don't know, does it make sense to do super resolution, then object detection or super resolved image, or to train a network that internally learns some kind of latent representation?
Yeah. Like reparameterization.
This is a question that I think it's open.
Okay, and the last question about the paper, which I tried to carefully read, is that when you compared your model with all the other algorithms, and the paper was published in 2023, I saw that most of the algorithms that you compared with were published between 2015 and 2017. So it seems like after 2017, there were no interesting solutions to compare.
Not exactly. So actually, yeah, until 2020, there were a lot of papers that they were working on deconvolution, super resolution, and also you need to understand we were trying to compare with methods that somehow we can compare, because it wouldn't make sense to compare our network, which is general, can be applied to different problems, with a network with 100 million parameters. Because yes, now there are also, based on diffusion models, deep learning networks that they can do amazing things, but they have like 500 million parameters. So it would be, it wouldn't make sense to compare. So we try to find like the current state of the art, but with the limitation that it's comparable. Because you need to understand also, our network, we trained it actually for different problems, and we deployed it to different. So because, as I said, the image prior we are learning is task agnostic. It doesn't care. It doesn't care the problem you are trying to solve. So actually, you can train it for one problem and then deploy it to different, as long as you change the data fidelity term. So this is another advantage, because most of the networks, they're task specific. They were designed to do this, and they cannot. If you want to do another task, you have to retrain. In our case, you don't.
Yeah.
So you can see it more like as a Swiss knife. It can work on different problems. It's not going to be state of the art, but it's going to work equally well for problems that otherwise you would need like a very specialized network.
Okay, thank you. Maybe we have questions from the chat or
other questions at the end of the talk. So,
okay. So I can move to the next.
yes.
Okay, so. Okay, so the next part of the presentation is about robust model fitting. So actually, the motivation for this work was the camera pose estimation problem. So the camera pose estimation problem appears in computer. It's like one of the core problems in computer vision. And so what it is, I have a set of images of the same scene taken from different views, and you need to be able to recover the camera poses. So the information, like the rotation and the relative pose of every camera for the corresponding image. And this is very important in many different applications, from robotics, VR, AR. I mean, because you need to know, you need to localize yourself where you are in the space, right? So this is actually one of the most important problems in computer vision. And obviously, it's not an easy problem. So typically, in order to be able to solve this task and recover the positions, you need to solve it in stages. So the first stage is that I have this series of images, and I try to extract key point features and match them across different images. So based on the matches, then I solve based on the matches of two images, I solve the so-called two-view geometry estimation problem, which I will explain. And after that, you have an initialization of the relative poses, because if you solve the two-view geometry estimation problem, essentially what you are finding is the relative position of two cameras, right? So if you do that for all for different pairs, you have like the relative poses, but you have found them in a non-optimum way, because you find like the relative pose of camera 1 with camera 2, the relative pose of camera 2, camera 3, but not between between 3 and 1. So at the end, there is a joint optimization problem, which is called bundle adjustment. So there, essentially what you are trying to solve a nonlinear problem where you try to recover all the poses and all the 3D points, because remember, the key point matching corresponds to the same 3D point in space projected to two different image planes, which are the two different views. So now you are trying to, in bundle adjustment, you try to find all the cameras plus the 3D points that correspond to the matches. And this is a very difficult task, and it's highly non-convex. So it's critical to have a good initialization, because if you start from a bad initialization, then with high probability you are going to either not converge or find a very bad solution. So this is very, very important. So that's why we focused on the two-view geometry estimation problem, which is like critical. And the reason is also that right now, I mean, nowadays, a lot of research has been done on the feature extraction and matching. And actually now there are networks that you give as input, like different views of the same scene, and it's going to find you key point and the matches. So this is a problem that is well studied, and there are very, very good networks that they can solve this problem. On the other hand, for the robust two-view geometry, there is not a lot of work. And also, one of the bottlenecks is about the backpropagation, which I will discuss next. So for the two-view geometry problem, actually you need to estimate the fundamental matrix. So the fundamental matrix has information about the intrinsic parameters of the camera, and also it's used to enforce a geometric constraint between the matches. So for example, here, imagine that you have like 2 points on 2 different planes. And if the algorithm, the feature matching, extraction and matching algorithm has found that these are like a pair, then they need to satisfy the epipolar constraint, which means that if these 2 points are projections of a 3D point, they need all these 3, they need to lie on the same plane, the epipolar plane. So the fundamental matrix, actually we use it to express algebraically this geometric constraint. And this is the form. So F is the fundamental matrix, and X prime are the 2 points on the image planes. So the fundamental matrix is a 3x3 matrix. So it has 9 degrees of freedom. But actually we know that it's a rank 2 matrix, so, and we cannot recover also the fundamental, we can recover the fundamental matrix up to a scaling. So essentially there are 7 degrees of freedom. So there is the 7 and 8 point algorithm that we can use to estimate it, which means that we need at least 7 matches between 2 images. So when we have like a set of images, we pass it to some engine that, or a network or an algorithm that will find us matches, and we need at least 7 in order to be able to estimate the fundamental matrix. So if we have, typically we use more than 7. So if we have, let's say, n set of matches, then the classical, the standard approach is to try to recover F by solving a least squares problem. So essentially what you are doing is A times, so you rewrite actually this constraint in terms where you express F as a vector, so you vectorize it. So if you do that, you end up to, because this is a scalar, but imagine that now I have n points. So I have a vector, n times 1, right? So I can rewrite this as in this form where F is the vectorized version of the fundamental matrix. So now, I mean, the idea is that, okay, typically this should be 0. So I'm trying to minimize the sum of the residuals, because if Ri is AIF, so essentially it's one constraint for one pair of matches, this would be the residual. I want this to be as small as possible. And this will give me F, the fundamental matrix, that explains the data. So essentially, this is a model fitting. I have a model for the fundamental matrix, and I try to find F, this fundamental matrix that minimizes the total residual error, right? Now, the problem is that actually we don't have the ground truth matches. We don't have like 2 points in the different views that we are sure they are really matches, but we have the outputs from either a classical technique. I mean, typically you do shift features and you do matching on these features, or you have a network. I mean, one very good network which has high accuracy is Lofter, but all of them, they have outliers. So they are going to give you matches which are not real. I mean, they are not really, they don't correspond to the same point. This is like an error of the algorithm or of the network. So these are called outliers. And the problem is that if you use the classical 8-point or 7-point algorithm, when you have outliers, you are going to have a huge problem in the recovered model. So the solution is going to be bad. So, and here there is an example where we are trying to do a linear fitting. Imagine we have this data, and these are outliers, and we want to fit a line. So if you try to use L2 and fit the line by minimizing the L2 norm of the residual, and you have outliers, you see that actually, even though the real line is this, if you do linear regression with L2, the recovered model is going to be completely off, which means that actually this approach is not robust to outliers. So it's very important when you are doing model fitting to have a method that it's not going to be heavily affected by the presence of outliers. So you expect that in the case that I don't have outliers, I can accept a small error, because in the L2 scenario, if you don't have outliers, the result is going to be exact, right? But if you have outliers, it's going to be very bad. So then we have to make a compromise and say, if there are outliers, I will get a very good model. If there are no outliers, I might not get as perfect results as the L2. So this is a small compromise you make. Okay. To deal with this problem, actually, there is a very popular technique which is called ransack. So the way it works is that I have all the data. So I randomly get a subset of this data. I solve the problem as if all these were inliers. And I score my model to all the data. And I do that for different subsets. And at the end, I choose the model that better explains all data. Unfortunately, the problem of ransack is that it is stochastic in nature, because you are doing this random sampling to get subsets. So our goal eventually would be to have a network that does feature matching and extraction, feature extraction and matching, fundamental matrix estimation, and then bundle adjustment, and be able to backpropagate, because right now the feature extraction and matching networks, they are not trained on the camera pose loss. They are trained on like intermediate losses. And this is what we were discussing before, Andrei. So if you want to solve this problem, it's better to do end-to-end training, right? So unfortunately, when you're using Ransack, you block the flow of gradients, because for bundle adjustment, you can use implicit differentiation. You say, okay, I solved my optimization problem, I reached some stationary point, I can backpropagate. The problem is with Ransack, you cannot do that. Of course, there are variants that they are differentiable, but it's very hard to train them because they require a lot of tuning. Sometimes the training fails, so it's not an easy task. Okay, so our approach is, instead of using Ransack, to do robust model fitting. We still try to find the solution by minimizing some loss, but our loss should be robust to outliers. Again, you can see here what we mean by robust to outliers. L2, if you plot it, it has this inverted bell shape, which means that if you have an outlier, which means that the residual it's further than 0, the penalty increases almost exponentially. So the higher the outlier, the more it affects, the more it's penalized. But by penalizing more the outliers, we are going to have a model which is heavily affected by the presence of the outliers. So the idea for a robust estimation is to have a loss function that doesn't overpenalize the outliers. It penalizes them, but not like in such an excessive way. And of course, here you can use again these LPP norms that I was saying, that depending on how you choose P, you see that actually it takes a different form. And as you go far from the origin, the penalty is almost the same. Either it's a very huge outlier or a medium. This is why we say it's a robust loss, because it doesn't overpenalize. Okay, so based on this idea, now what we said is, okay, let's create a layer, a network that can solve this problem robustly and also will be differentiable, so that we can allow to train also the feature matching network for the camera pose estimation problem. And as before, I mean, this will remind you the previous form. What we have, we also include some weights. And again, the idea is that in the scenario where we have the matches, if you measure the residual, it's going to give you some values. So now what we want is, like, if we have some residuals which are high, we don't care about trying to set them to 0, because trying to set these to 0 means that our model tries to explain them, but these are outliers, so we don't need to explain them. So, and actually what we can do, also, we can set weights for these residuals small, so overally, we don't, when we try to minimize the overall function, the model is not going to pay a lot of attention to these outliers, right? And again, here, I mean, the question is, okay, very nice, how can you solve that? Because it's one thing to, like, design a loss, and another thing, how to efficiently minimize it. And again, the idea is that, similar to what I described before, essentially, you are, again, trying to find some upper bound. So the important observation here is that actually these weighted LPP norms, you can express them in a variational form. What I mean is that you can express them as the minimum of another function. And this another function now has two parameters. Phi, which is, like, let's say, the one vector that we are trying to recover, and beta are auxiliary functions. So based on the on this upper bound, you can see that for any beta, this function is always an upper bound of the original loss function, which means that actually there is one particular beta for which we obtain our function. So based on this upper bound, we take this variational form. And the reason that this is always upper bound is, you see, all these terms are positive, right? Since they are positive, in order to recover R is a minimum of this function. Yeah. Okay, yeah, I will finish. So how we solve it, like after we define this, after we observe that we can express this loss function in this form, what we say, originally we want to minimize this problem. But instead of minimizing that, we have to minimize this auxiliary function. And now the constraints are two variables. We have phi and beta. So what we do is like coordinate descent. So alternating minimization. We fix one set of parameters, let's say phi, and we are solving for beta. Then we fix beta and we are solving for phi. And because this is a coordinate descent method where both problems, actually you can solve them in closed form, again, we have this update rule. So essentially what this amounts is that now we are just solving a homogeneously square problem, but iteratively, where we have like one matrix that changes in every iteration. So this formula is similar to the original problem with L2 regression. The main difference is that it has some extra matrix, but this extra matrix depends on the solution of the previous iteration. So it's like solving adaptive L2. Right. So based on that, actually we can solve efficiently this robust estimation problem by doing this recursion, where we solve several times this L2 regression problem, L2 estimation problem. Of course, as I said before, we end up to the same problem. Now, if you unroll, because if you see here, if you unroll, then you need to keep the intermediate results, and on top of that, you need to backpropagate through SVD. And SVD is notorious for backpropagation, it's very unstable. So the question, how can we deal with that? Again, the trick is that, as I said, because this is a block coordinate descent method, and both subproblems we solve them in closed form, we have the guarantees that we are going to reach a stationary point. So again, we treat this as an implicit layer. We don't care how many iterations we do to solve it. We know that after convergence, we are going to have a stationary point, and we use the first order optimality condition to backpropagate. So it's exactly, and this is the connection between the two parts of this work, that in both cases, even though the problems are different, we can use the fact that our optimization algorithm is going to converge to stationary point, so we don't need to do the classical unrolling and backpropagation through time. We can run it for as many steps as we need, and then backpropagate in one step. So the overall pipeline that we have is like the feature extraction and matching that I say, in particular in our experiments, we used Loft, which is like a state-of-the-art approach for feature matching. Then we have initialization, which is essentially we're using a weighted version of the 8-point algorithm, L2. And then we have, again, a refinement network, which is a weight prediction network based on the solution. And we do our algorithm based on the weights from the previous solution to update it. And we run that a couple of times, I think 2 or 3 times, because in every time we get an estimate of the fundamental matrix and we refine it. And based on that, we can extract the relative poses and cameras, which we use at the end for the bundle adjustment to do the joint optimization. And actually, the results here are very interesting because we tried both for indoor and outdoor data to do the camera pose estimation, and compared it with state-of-the-art methods, like not only RANSAC, but MagSac++. It's a variant of RANSAC, which it's considered to be the current state of the art, plus some learnable techniques, and we get extremely good results. And the cost actually, because this method, it's much easier than the previous, because here you have a very small linear system to solve. So you solve it immediately. It doesn't involve like million times millions matrices. And another interesting, and this is my last slide, another interesting thing is that when we train our network to do this fundamental matrix estimation, and we do end-to-end training, fine-tuning, so we have loft, we solve that, but we backpropagate the gradients to loft. At the end, you can run loft, and you can see that actually the network has even improved by itself on the task of matching. Because in this example, for example, this is loft, the original with the pre-trained weights, and you see that there are like these outliers. And when we fine-tune it or by training our network, you see that actually now you have a reduced number of outliers, which actually verifies that it's better to train the network for the final goal. And this is not even the final goal, because we are using like the fundamental matrix. The final goal would be to train it also for the camera pose, the final, like after bundle adjustment. But here, I mean, we did that because it was like also computationally easier, and to make the point that training end-to-end actually can also benefit the network, the extraction network. And yeah, that's the end of my presentation. So the key message of this presentation actually is that the concept of implicit differentiation is very powerful, because you can use like classical techniques to solve an optimization problem, and then you don't have to, because in the past, what we did, like a lot of networks, they are inspired by optimization methods, but typically they did unrolling, and because you cannot really run a lot of iterations, you say, okay, I will unroll to 10 iterations and I will backpropagate. But actually with implicit differentiation, if you carefully design your optimization method and you know that it's going to converge, then you can run it. That's why we say infinite depth networks, because in principle you can run it like as much as you need, but then you can use this trick to differentiate on the optimality condition. So it makes everything much simpler. Thank you.
Thank you. Stamatis, thank you for such a great talk. And before we move to the Q&A section, do you have a chance to ask you, Stamatis, any questions as a...
I also prepared several questions for this topic. However, I will select the most short ones. I think it will be to give time for other questions. So first of all, there was a step in the overall architecture on the previous slide, as far as I remember. Yes. Here. In the paper, you said that F0 and the initial solution is one of the most sensitive parts of the architecture. So it means that selection of this G-init, the initial solution approach or model, is very important for the overall architecture.
This part actually what corresponds. Because if you see in the previous slides, I mentioned about this 8-point algorithm. Typically what you do is also you weight that.
Yeah.
So here what we have, we are using, again, we have to predict the weights to do a weighted, but the problem always, when you have like an optimization method, because this problem is not going to have like a global minimum. So it depends how you initialize it. So it's critical also to have like some good initialization.
So just to find the best suboptimal.
Yeah. Not the best, but not like something very bad. Because if you start from a very bad point, then unfortunately it's going to. Because you see, we have also, in our case, we have this P value which is smaller than 1, which makes the problem non-convex, plus the weights. So it's a little bit, you need to be a little bit careful. So it's not okay, out of the box, I use it
Mhm,
and
yeah.
magically works. But so you need to be a little bit careful.
And this actually leads to this number of iterations in iterative homogeneity least squares, yeah?
Yeah,
So,
yeah. So,
there is a dependency between how you select the
yes,
zero.
because it's like if I start from a good solution,
Mhm.
then I will converge faster.
Mhm.
If I start from a bad solution, I will need more iterations to because the whole thing is all these iterative optimization methods, they need some initialization.
Mhm.
If you have, it's the same in like in conjugate gradient. If you can start from
Yeah.
zero solution, it will take more time. But there it's also you have guarantees that you are going to find. Here, because it's non-convex, it's a little bit sensitive, I mean highly sensitive to where you start. If you start from a bad starting point, then you might end to a bad solution. So in general, but this is not a problem of this method, it's a problem
Overall, yeah,
overall,
yeah.
yeah. And in bundle adjustment, for example, if you start from a bad solution, bundle adjustment is going to fail because we are talking like about a very highly non-convex and high dimensional problem. So you need to be actually in the literature, a lot of effort is devoted to how to find good initializations because of the sensitivity of the problem.
Mhm. Okay, and the second question is about the improvement of the method. If what if we work not only with two images but with multiple images? It should grow exponentially, as far as I think.
Yes, so typically you don't. So that's why we're talking about the two. There are the epipolar constraints for two images.
Yes.
There is also work that involves three images. So there is like a triplane constraint. This we didn't really touch because the most common, what they are doing, they are taking like two images, they find the relative position. Then you take one of the two to find for the third, and so on and so forth.
Okay.
Even in bundle
Like
adjustment.
a sequential order.
Even in bundle adjustment, you don't do joint optimization. You do somehow sequential. You have like a subset, because otherwise, if you have like a lot of unknowns, the problem becomes like very difficult to solve. So they try to split it in some part, solve a subset jointly, and then add because otherwise
It's better in terms of convergence, yeah?
Yeah, and in convergence, but also computationally.
Computationally, of course.
Because otherwise you increase the number of unknowns drastically.
Okay, thank you. Very interesting topic, and especially for computer vision specialists, I think this such classic theory, such classic approaches are still developing, and it's very interesting to listen such topics.
You know, actually, the funny thing is that when I had this idea because we were working for the previous work, and then I said, okay, these robust functions, they cannot have just one application. I'm pretty sure they should have application. And then it came to my attention because I was never working like on camera pose estimation. But then we were working on a project for AR and 3D reconstruction. And then I said, okay, actually, I didn't see in the literature, most of the people were using Ransack, Colmap, and it came to more, and I wanted to have like a network to be able to train it end to end. And the problem was always like there in the two-view geometry subtask. And I said, okay, but actually this robust matching, robust fitting, it's a very good use for this problem. And actually, there are a lot of works on the 90s about M estimators, robust M estimators, but there was not really a catch up on the deep learning. And I thought that this would be, you know, a nice direction.
Okay,
Thank you. So now it's time for questions for audience. So please raise your hand here, and the mic will be given to you in 3 seconds. I hope.
Thank you for the presentation. It was very well made, actually. Which software did you use to make it for illustrations, for math notation?
So this is PowerPoint, but the math equations, there is a, there is a small tool, it's called LaTeX, if you are working on Mac. So it can make SVG files and you can include it. So, yeah.
Yeah, okay, thank you. Could you please open slide number 34?
34.
Did I understand it correctly that for p equal to 1, it's equivalent to quantile regression and specifically to median regression?
So, yeah, p equals 1 is the classical L1 loss, right? Yes.
And in quantile regression, it's a common problem when the optimization is quite long because some closed form are not developed.
Yes, so this is the point. Again, you have the same problem as what I mentioned before. If you have a loss function, first of all, L1, the problem is not smooth on the origin, right? So the problem there is actually in practice you cannot differentiate it. But what we do, we smooth it a little bit there. That's why you see here we have a small epsilon. But if you try to do classical gradient descent, this is going to converge very slowly. That's why there are these techniques that I told you. In MM, you can efficiently upper bound it with an L2, and this actually converges much faster. So there are a lot of papers, at least in the domain that I know, in image reconstruction, this, because L1 is, in ML they call it lasso, right? In my field, we were calling it like L1 regularization. We had total variation, which is like also L1 or the anisotropic. So this technique actually it has been shown to converge quite fast and without any issues.
Thank you. And my question is, could this be applied for a regular quantile regression? Because it's a widely used method, and if it can be a bit more faster, it
like which method?
Quantile regression. Quantile regression.
Quantile regression.
Yeah.
So how the terminology I am not familiar, but how does it work?
It's one of common methods of robust regression when we predict not the expected value of a random variable, but we predict conditional quantiles. So we predict not the expectation, but median, or for example, 90 percentile.
Okay, yeah, I'm not sure about, yeah, maybe, but have in mind that in this problem, you try to minimize it subject to a constraint.
Yes, it's used so-called check clause, which looks like this check with p equal 1.
Mm-hmm. But in general, so actually in our work, what we did, this iterative homogeneous least squares, is a generalization. So we can minimize any function of the form LPP for P from 0 to infinity.
Okay, thank you. And my last question is about pose estimation. You told that it's important for mobile phones, for VR, AR, robotics, but as far as I know, all edge devices now have lidars, accelerometers, gyroscopes. Is this...
Not really. Tesla, for example, they don't have lidar. They have cameras.
Eight. I guess they have 8 cameras on the machine.
Yeah, but yeah, of course. But still, you need to do. Okay, there, of course, they have like calibration, but in general, for example, for AR, there is no really other option than solving this problem. You don't have like lidar sensors for AR VR, right? For autonomous driving, yes, you have more sensors, but even in this case, lidar, okay, they use it for depth, right? The problem with lidar is that they are more sparse measurements, so they always work in tandem with camera. It's not like that you can just use lidar and everything is fine. So in general, camera pose estimation is very, very relevant problem, even when you have like extra sensors.
LiDAR usually has much less resolution because
Yes,
it is not,
and
cannot be
it's
used
also- yeah, because
without
it's like
cameras.
sparse. So the points are much sparse. Of course, it's more accurate, but it's much sparser.
So these, well, I would say, intricate algorithmic methods are actually used in edge devices, like mobile phones, VR headsets, and well,
LiDAR. They use. You mean they?
I mean pose estimation. So
Pose estimation.
yeah.
Yeah. So again, I'm not an expert in pose estimation. I found it just an interesting problem because we were working back when we started working on this project. So I haven't been working for many years on this. It was like mostly because we were working on 3D reconstruction with Gaussian splats, and the classical technique there is call map, where you have like a sequence of images and you want to extract the camera poses, because otherwise, so the starting point is the camera poses. That's why I mentioned the AR and VR, because now with 3D reconstruction using Gaussian splatting, this is like one of the prominent applications. And always, this is the huge, because in practice, you don't have any special equipment. You have like a bunch of images. Let's say I go with my phone, I take some images, I give it to you, and I say, okay, now you are the expert, do a 3D reconstruction. Good luck. I mean, you need to do camera pose estimation because you don't have any other metadata or other information. For robotics, yes, probably you have more sensors. It's like more well designed, but when you have like a user application, you cannot afford to have like very specific sensors and a setup that the user is going to respect. It's like more free.
Okay, thank you.
Next question.
Yeah, thanks for the presentation. My question is, how tight is the connection of your implicit layer formulation to the regional deep equilibrium networks and stuff they do? Do you have like any additional constraints? And did you experience any problems regarding convergence during your experiments? Yeah.
Okay, so yes, actually that's a good point, because there is this line of work. Actually, it's related to deep equilibrium networks. What is the main idea of the deep equilibrium networks? That it comes with the idea of implicit layer, that a direct layer is a layer where I have some input, there is some instructions inside the layer, how to process the input to provide me an output. While in the implicit layer, it doesn't follow this norm. It says that I have an input, I should have an output, and the input and the output should satisfy some constraint, right? So in deep equilibrium networks, they don't have actually the constraint. They say that the network is going to converge to some stationary point, but they don't have an original function that they don't have any function to minimize. They use this idea like in an abstract way, that I have some kind of recurrency, I have a network, and this, after I feed the input to the output several times, is going to converge to some stationary point. First of all, a recurrency is not always guaranteed to converge, right? So there should be some conditions about the Jacobian of the system. So it's not really, so the difference. In our case, we have a very well-established constraint and a very established algorithm that we know we are going to converge. In the deep equilibrium networks, they are based on this idea, but they don't have any guarantees what they are doing is going to converge and what they are minimizing. So there is not like, you understand my point? There is not some concrete function that they are minimizing, and then they have some proof that is going to. Of course, there is a line of work that they say about monotone operators and this recurrency is going to converge, but it's a little bit more abstract. Here, it's very concrete. Of course, they are related because both of our works, they depend on the implicit function theorem, But in our case, we have a very concrete objective, an algorithm that we have guarantees that it's going to converge, so it's going to satisfy the implicit function theorem. While in deep equilibriums, it's more like a motivation. It's not really that they have a network that is going to converge to a stationary point. They hope for. If you read the paper, I mean, they say, we hope that it's going to converge, not going. There is no guarantee.
Okay, thanks. And a little follow-up. So am I right that generally methods used to optimize deep equilibrium networks are not applicable to your case, like Providence methods? Or like
No. They are using Anderson method. So this is look. In their case, again, because they don't have a concrete optimality condition, I mean, they try like a generic method. In our case, because we know exactly what we're minimizing and what is the optimality condition, actually, in our case, we use CG for the inverse, for the optimality condition, for the diffusion, for the backpropagation, which is much faster than the Anderson method. And this is because we have like something concrete. There, it's like more, okay, I have a network. This network somehow models some recurrent system. I don't know what the network will learn. Here, it's like very, very well defined.
Yeah, okay, thank you very much.
Other questions?
Yeah, I have a question about the first paper. So you propose a problem with a like linear degradation operator, and you solve it with your learnable regularization. Do you compare your results? Do you have an explicit does your solution provide an explicit form of this linear degradation operator on estimation of it? And do you compare? Like, no, well, you.
What do you mean? Because I'm not sure I follow correctly. Yeah, we have this linear, this is the assumption, right? Because we're dealing with linear inverse problems. Unfortunately, non-linear inverse problems are very, very hard to deal with. And even if you have a non-linear, the standard approach is to try to do a linear approximation.
I understand. Yeah.
Okay.
Yeah, I understand it. I mean, so you have a blur kernel, you convolve it with your image, you get a blur image. Do you explicitly like have an operator? Like, does your method, after it converges, provide an operator, a blur operator that was convolved with the image to get the blur image? Or
yeah, okay, I understand your point. Yeah. So, look. The problem of deconvolution, there are two problems. It's like deblurring and blind deconvolution. In blind deconvolution, not only you need to recover your signal, but you need to recover also the blur kernel. But typically how this problem is solved? Originally you assume some blur kernel and you find a solution. Then you fix your solution and you find your blur kernel. And you do that, right? So in our case, because the paper was more generic, like how to solve this type of forms, we didn't really pay a lot of attention. What we did is we used an external method because we have results with real blurred images. We feed this image to external method to give us a guess of the kernel. And based on that, we did of course, if the guess is bad, of the blur kernel, the reconstruction is going to be also bad because it is not faithful to the model. But this has nothing to do with the method. It has to do with any method that you misuse the blurring operator is going to give you bad results because it's not. I mean, the model assumes that this is something that should be known.
maybe it can be more or less robust to it.
Yeah. So yeah, there is certain robustness because the results I show here are with real kernels, and of course, what we estimated is by far not the ground truth. But you see that actually there is robustness in that.
Yeah, of course, yeah, I see. And follow up, so in the year of 21, there was a paper which approximated this blur kernel with ReLoop plus FFT, and
There are a lot of different.
and they put it in ResNet block, and they got some also deep learning results. Didn't you compare with this paper?
Look, we have compared with a lot of methods, but again, I mean, what is the problem of on blind deconvolution is that you read a paper, they say that their method is amazing, and then you try it, and it's like very, very bad results.
Yeah.
So we cannot even include them in the paper because we don't know if we used. Of course, they provide some code. Some they don't provide code. So it's out of the question to compare. Some they provide code that we tried and it gives very bad results, and then we don't want to include in the paper because maybe the authors will say, you didn't fine tune. We used this special parameter. So, but we actually have tried with a lot of different methods. But again, blind deconvolution is very special in the sense that you have like two unknowns. Not only the signal you want to recover, but you have to find the gradation. The same with super resolution, but super resolution is a little bit easier somehow. But blind deconvolution, there are a lot of works, but the bottom line is how they solve it. I guess a solution, I fix it, based on the solution I find the kernel. Then I fix the kernel. So it's alternating optimization. You cannot do something better. This is like the...
Okay, thank you. I understand.
Okay, thank you. No time for the questions, but we do have questions from online audience. So we will send you if you don't mind, and then post your answers.
Yes.
And let's thank one more time Stamatis and Andrew for today. Great lecture, great talk.
Thank you very much.
Thank you.
Thank you, Stamatis.
And this is end for today. See you next time on AIRI Seminars. Bye.
Goodbye.
Thank you, guys.